So we start again this afternoon session with a talk from Alex Kontorovich from Rutgers University and AWS. He will talk to us about the prime number theorem and the real analysis game. Please, Alex, go on.
Okay, thank you so much. It's a great pleasure for me to speak with you this afternoon for you guys. I'm sorry I couldn't be there in person. I was just in Italy 2 months ago, but it's the last week of class. And so um, please also, I don't know how, but if you could interrupt at any time and ask questions as much as possible, I would love for this to be interactive. So um, I don't know how to facilitate that, but hopefully someone can alert me if there's a question in the audience and I can stop and try to take any questions. Okay, so yeah, let's talk a little bit about these two projects. So the first is the prime number theorem. So this is something that Terry Tao and I are co-organizing. And the goal, the sort of medium-term goal, I would say, is to get the Shebetarov density theorem formalized. Because that'll be an ingredient in Fermat's last theorem. Of course, it's something that was known before 1980, so maybe it's not actually strictly necessary for Kevin's project, but still, it was something that we thought we could do. It's not something that's formalized in any system right now, as far as I'm aware. Maybe someone will tell me otherwise. And when we were talking about this, we said, well, we don't even have Dirichlet's theorem for primes and progressions. We didn't at the time. We do now. And before Dirichlet's theorem, we didn't have the prime number theorem. So we wanted to jump right in. Of course, the prime number theorem has been formalized many, many times before. It's one of the first things that Jeremy Avigad did in Isabel 20 years ago. It's kind of hard to imagine that that's when that was. And then it was formalized in Hall Light and MetaMath, again in Isabel, doing Newman's proof instead of the Erdős-Selberg elementary method. Newman's method is kind of what I'll call Fourier analytic. Anyway, and we wanted to do it in a way that would extend to much more general settings because our target was Shebetarov. Now that's the medium target. The long-term target is something like, let's formalize all of Ivanets-Kowalski and have the full, all the tools of analytic number theory with lots of tactics and everything ready to go. Of course, that's the long-term dream, and the medium-term dream is Shebetarov, and the short-term dream is the prime number theorem. And this was also an experiment in large-scale collaboration. This will be not news to anyone in this room, I think, but at the time, Terry had just completed the polynomial Freiman-Ruja formalization, several weeks after the paper was posted to the archive. And of course, we're building on top of many, many projects of a similar vein, sphere aversion, liquid tensor, the formalization of the definition of perfectoid spaces, and so on. And of course, we're using Patrick's blueprint structure. Now, I'm not going to say too much about blueprint because Pietro, you're going to say a lot more, right?
Yes.
Okay, great. So, but of course, I think the crowd is familiar with blueprint. Obviously, everybody's familiar with GitHub and Zulip. So these were sort of the three components: the GitHub to keep track of the code, Blueprint to keep track of the mathematics, and Zulip to keep track of the human beings involved in the formalization and sort of organize everyone. So one little innovation, which I think is, well, we'll hear more from Pietro, but I think is becoming standardized, is that originally the blueprint was meant to be a standalone tech file, and then you just make the tech file that generates the blueprint, and then you have a separate file where all your lean stuff is. And to me, it was too hard to keep track. Like you make some change in the lean as you're formalizing, and all of a sudden you have to remember, oh, where is that exactly in the tech file, and be able to jump back and forth. And so Ian Yausling and I sat down and just wrote a little scraper. It's a very simple thing where you add these delimiters to your lean file, and that will be scraped out into a separate tech file. What I didn't anticipate at the time was how useful that would be when having GitHub Copilot turned on in your VS Code in the background, because as you can see here, I've written a theorem in tech, and my cursor is sitting right here, and Copilot is suggesting an auto-formalization. So this was already 2 years ago, before the explosion in auto-formalization we're seeing today. It was already drastically speeding up my workflow in designing the blueprint to have this running in the background, although sometimes it got in the way and I had to turn it off and say, shut up, I have to think, you're going too fast and saying the wrong things. So you're actually slowing me down. Anyway, by the way, there's a version that I saw on Paul Nelson's setup in Emacs where it's exactly this, except you don't see tech here. You literally see what we would say is compiled PDF in the same view as the lean. So that's really beautiful. It would be amazing to get a VS Code version of that somehow. Anyway, maybe that's coming in the next, maybe I should just wait 45 minutes for Pietro's talk and we'll see something like that, but um, something to play with. So how's it going? So it was open to the public, beginning of 2024, and about 2 months later, the first proof of the prime number theorem was completed. So, and even in those 2 months, it wasn't a race because we were really interested in um, giving ourselves an excuse to get a whole bunch more stuff into MathLib that wasn't there. So as I said, the short-term phase is the prime number theorem itself, which itself broke down into three sub-phases. The first is using Fourier methods. That's because Michael Stahl had already reduced the prime number theorem to a Tauberian theorem, namely the Wiener-Ikehara version of the Tauberian theorem. You never, I'm sorry if there are people in the crowd who aren't analytic number theorists. Anyway, I'm not going to say anything that's anything too complicated, but this theorem allows you to prove the prime number theorem without ever going past the one line. So you're staying within the realm of absolute convergence at all times. Then the second attack was that we anticipated from the very beginning was to develop Mellin transforms a little bit farther than they had already been developed by David Loeffler, and pulling infinite vertical contours, going past the pole, picking up a residue, and that'll get us a error term that's as good as any application to as good as the vast majority of applications, let's put it that way. And then the third phase was to get the classical, the Hadamard-Delahaye-Poisson error term with a savings of e to the root log x. And we anticipated at that point that we would have to face Hadamard factorization, or actually local versions, which, Hadamard factorization, the hard thing about it is you have an infinite product of these terms, and how do you even set this up in Lean? And there were a lot of complications. The Hadamard factorization still has not been done. The local versions now have been done. That's the Borel-Carathéodory theorem. So maybe I'll say more about that, but probably not. Anyway, so that's phase one. And I should say that when we were sort of 3/4 of the way done with phase one of phase one, there was a post by Song and Yao who jumped straight to step 3 and formalized it in Isabelle. Of course, they're building on top of a much bigger complex analysis library that exists there, and the prime number theorem in various guises had already been formalized as well. So so we're still catching up to Isabelle in some sense. We're far behind Isabelle in how much complex analysis Lean has. Okay. And it was a great excuse to get lots of students and postdocs involved in learning Lean and in learning formalization in general. And so from when we finished phase one to when we finished phase two, we really took a slow burn to try to get a lot of people involved. This culminated in the Simons Foundation sponsoring generously a workshop that took place in June in 2025. And I put a link here to, if you just go to the Lean community blog, you'll see a list of all the talks are posted, all the videos are posted, and lecture notes and so on. It was a meeting not unlike the one you guys are in now. We had 2 weeks in New York City, so it was a very luxurious meeting actually to get an opportunity to get a whole lot of stuff done. We brought in something like 50 postdocs and graduate students from around the country and around the world. And the progress that we managed to push in that week was such that, once all of the last PRs came in a few weeks after the workshop was over, I just said, okay, we're close enough to the medium PNT, let's just finish it off. And it was done in, I think, July of 2025. So, and it got this, as I said, slightly weaker savings of e to the log to the 1/10 instead of e to the root log. So that was, and so we were gearing up for step 3. In fact, there was in our Zulip thread, there was a participant who had claimed the Borel-Carathéodory theorem, which was sort of the main bottleneck for starting on step three. Step two really puts together all of the complex analysis that you need, except for this Hadamard factorization. And so once you get that, everything else sort of falls into place, at least in principle. Of course, then you start formalizing and you realize what all the missing pieces are. But then we were very happy and surprised when we heard from Math Inc. that their Gauss solver managed to, so it automated all of the lean proving, but it did so iteratively with Jared going back and forth whenever it got stuck and putting more details into the blueprint until the solver could, I would say, quasi-auto formalize the proof in that Jared was driving the natural language part of the discussion. Anyway, yeah, to go back to the medium prime number theorem, the solution was a mix of large-scale human collaborative effort over a dedicated Zulip channel, as usual. As I mentioned already, I used Copilot quite heavily in speeding up the writing of Tech and Lean. This was before GPT was pretty useless at the time, and Claude wasn't, if it was out yet, I wasn't aware of it as something that's useful. Today, it would be much faster to do all of these things with AI support. Of course, now we have Harmonic and Alpha Proof and Gauss and Aleph and all these systems. And the last thing was I was very fortunate to be on sabbatical at the Institute for Advanced Study in Princeton, where DeepMind came and visited us for a week. And so there I got a chance to try out some of the goals with Alpha Proof. And I was just shocked. I was really blown away by what those systems could do. Now that seems antiquated. It was 6 months ago. And almost Claude could do the things, can now do, Claude off the shelf can now do the kinds of things I was seeing there. But just to show you what that looks like, so here's a sample. I don't know, can you see this in the room? I'm sorry for the people in the back. It's nice and big on my screen, but should I try to blow it up or you can see it?
It's fine.
Yeah, okay. So this is, some simple have statement. What I like to do is scaffold the proof with a bunch of have statements, check that the have statements actually prove the main theorem I'm working on, and then go, one by one through the saris and start filling them in. And of course, you find that you didn't formalize something exactly right, and you have to change the statement, and then that cascades down below. But here's Alpha Proof's solution to the following have statement. So I wrote the have statement, Alpha Proof wrote the proof, and it's just that the zeta function blows up at 1, and so in a neighborhood of 1, of course, you have to not include 1. It's always, has absolute value at least 1. That was some stupid ingredient in some little sub-argument. And this is what it spat out. And at the time, I was really blown away by this because, well, it sort of learned its own language. I mean, I don't know, maybe there are people in the room who can read this. For some reason, it loves to use the dummy word and for its variables, for its random variables. The main crux is right here. There's already a theorem in the library in MathLib that the zeta function has a residue of 1 at s equals 1. So that's the crux of what it's using, but somehow it has to get there, and it's got these, up arrow underscores. I mean, it really, because of this reinforcement learning, the way that it was trained, it has invented its own language. But as far as, of course, this would not go into MathLib, but as far as just racing to a proof of something, if you're interested in checking if your little lemma makes any sense, this is an incredible tool to have at your fingertips. So, so I'm really excited that the API is coming out, hopefully very, very shortly. So, it's great to be able to have this kind of thing. Of course, it would be better if I could understand what the proof was. And so just compare that to what Gauss, and now I've had a chance to play with things like Gödelprover, the open access one that you can run anywhere. The weights are, everything about Gödelprover is open access. This is just a much more pleasant proof to read. This is something about you have a function that's analytic on a closed ball. This was all completely formalized by Gauss. I think Jared didn't touch the lean at all. He only interacted with Gauss through through the blueprint in natural language. So, it's introing something, and then it's saying, there are all these have statements. This is in a metric ball, and then R1 is less than R. Okay, so I can really tell what it's doing, and it's even kindly adding some comments for me. So it's giving me a nice proof outline. So just to keep in mind these differences of how different AI systems work. So again, the early phase of the project was all human collaborative effort over Zulip, and the more time progressed, more and more chunks could be done by automation, alpha proof, until finally Gauss just did the entire third step by itself. Regardless, the project was a great excuse, as I said before, to do some more analysis and get some more analysis into MATLAB. At the time, we didn't even have Fourier inversion. Now we do, thanks to Sébastien Gazelle. We didn't know that the Fourier transform of a Schwartz function was Schwartz. This is, of course, a very important just general theorem that we need to have in the library. And Sébastien and David Loeffler and Heather Macbeth and I contributed to this, and Vincent Pafara finally got this into MATLAB. We were also missing one of the still least developed of the late undergrad, early grad areas in MATLAB, namely complex analysis. So let's talk about that for a second. So just last week I asked Claude, okay, tell me what the main theorems are in a first year course on complex analysis or first semester course on complex analysis. It spat out all of these things, which I remembered from sophomore year when I took a complex analysis for the first time with Eli Stein. And yeah, that looked like a good list. And I said, okay, go look up what's in MATLAB now, what's available, and what still is not. And so it came back with these things that is this really proved in MATLAB? I'm just noticing that Hadamard's three lines theorem is here. Notice that Hadamard factorization, I don't even see it on this list. Anyway, I do notice the Riemann mapping theorem, and I know that Vincent Pafara had this nearly done 2+ years ago. So I guess for whatever reason, maybe it's making its way into MATLAB, but I'd like to see it there. And of course, the residue theorem, at least Claude says is not proved. I didn't see it either in MATLAB, but we have an attack on it from the PNT Plus project. So let me tell you about that. So, the residue theorem, I mean, depending on in what generality you want to state it, Cauchy's version, you need the Jordan curve theorem. And of course, that's another notorious thing that, someone could have years ago sat down and wrote out 10,000 lines of lean code, because that's what it took in Isabel when Tom Hales formalized the Jordan curve theorem there. But really, it should be a result in a computation in homological algebra or something. So people are waiting for that to be available to get just the Jordan curve theorem to get started. And so the standard way to bypass proving the Jordan curve theorem is to just do everything with keyhole contours. You can do nearly everything you want with contours that look like this. You want to integrate some holomorphic function on a disk, except it's not holomorphic at this point, and so you avoid that point, and you get a simply connected domain, and then you take the neck down to the width of the neck down to 0, and you basically show that the integral over the large circle can be zoomed into an integral over a small circle, where you use continuity and argue there. You really want to code up what integrating over all of these contours is? I mean, you can do it. It's not impenetrable. It would just be a terrible nightmare, and I don't want to do it. And so the final realization just before we started the prime number theorem was that I could do all the complex analysis I needed to for analytic number theory just using rectangles. And so, in fact, the test case for this was a PR of Ian Yausling and myself, that holomorphic functions on disks have primitives. Now, I'm talking about disks, but actually the way you make those holomorphic functions is by integrating over rectangles. This is like Morera's theorem. And we already had at that time Green's theorem, thanks to Yuri, in MATLAB. So we know that the integral of a holomorphic function over a rectangle is 0. And so what do you do with that information? Well, let's say you have a holomorphic function on a rectangle with some singularity inside the rectangle. What are you supposed to do? In the in the case of circles, you would cut into the circle and make a little loop and come back out. Here, there's a beautiful geometry that all of you know very well, which is that rectangles tile rectangles. Discs do not tile discs. And so all you can do, you can chop it into fewer than 9 smaller rectangles. I'm just drawing 9 for you for ease of exposition. And 8 of them have integral going to 0. You're just adding and subtracting integrals over the same region, so that's not changing anything. And any rectangle that doesn't contain the singularity, by Green's theorem, will have integral 0, and so you can zoom in, as usual, down to the rectangle. And so now you're faced with integrating a function that's like, 1 over s. Let's move everything to the origin. You have to integrate ds over s over a rectangle. Over a disk, it's very easy to parameterize and integrate, right? It's just epsilon times e to the I theta, where ds is also e to the I theta, so everything cancels out and you just get 2 pi I without doing anything. And then I saw this and I said, oh crap, we have to integrate dx over x minus I times epsilon. That's just over the bottom part of the integral. And maybe now we have to deal with complex logs, and that's a headache. And then I made the following trivial observation, that if you add the bottom and the top together, so this is the bottom and this is the top, and if you just combine these two integrals, what you get is a real valued integral that's just dx over x squared plus 1, which is arctan. And MATLAB already knows that. And so once I saw that, I said, okay, this really is a new way of proving these basic theorems in complex analysis, but they're very, very simple, and they use only the tools that are already available in MATLAB. And so if you so the bottom plus the top gives you a contribution of pi I, and of course the right and left side also gives you another contribution of pi I for your 2 pi I. So we do have a version of the residue theorem, just not in MATLAB. So what about pulling contours? Can we do that? So we wanted things like, transform Mellin inverses. We had Mellin transforms. I don't think we had Mellin inverses at the time. We now do. And we needed things like Perron's formula. So Perron's formula is an integral of this type. If you're not familiar with it from analytic number theory, don't worry about it. This symbol means you're integrating over the vertical line where the real part of s is equal to 2. In fact, anything greater than 1 will, greater than 0 here, will do. And the human proof is, you just pull contours left and right and everything's good. Can you actually execute this in Lean? And the answer is yes. And here it is. And pulling contours is nothing but adding and subtracting rectangles. And we know how to move rectangles through simple pulls and then do some simple limiting arguments. Okay. So that is now all in, well, it's not in MATLib, it's in the PNT Plus project. We also, this is another technical point, we systematically use smoothing. For some reason, there's this phenomenological aspect of analytic number theory where it's completely standard in modern analytic number theory to use smooth functions instead of explicit, some kind of like a function that is 1 and then it goes linearly down to 0 at the prescribed point and then remains 0. You don't do that unless you're proving the prime number theorem. For some reason, number theorists always have to go back to Riemann and the way things were done 150 years ago. So if you open up the textbooks for how to do this kind of Perron's formula, they would say you're integrating ds over s, which doesn't converge absolutely, so you have to chop it off at height t, and you get these really, really annoying factors to keep track of. And one little innovation was to prove the prime number theorem using the tools that analytic number theorists use everywhere else, just for some reason not in the prime number theorem. So if you see here, this converges absolutely. I have 1 over s squared in the denominator, so there's no problem integrating this and interchanging orders of integrals. Okay, so what's the upshot? It started as an experiment in formalization, in getting lots more analysis into Lean, and as something that was going to be very massively collaborative. It's still a very good mechanism, I find, for teaching newcomers. We have a whole group at Rutgers where we talk about math and AI and formalization, and projects like this one are seem to be very successful at giving people lots of small things to work on locally. Of course, when you're teaching people instead of just trying to do something, we're moving nice and slow. Speed is not the point of what we're trying to accomplish with theorems that have already been known for 130 years. But the more recent new paradigm is, of course, if you get your API from Aristotle or alpha proof or Gauss or Axiom or Aleph or Gödel prover, and et cetera, and more of these are coming online every day, it seems. Um, the experience is it's not massively collaborative, actually. It's just one person sitting in his or her office working alone with AI, sending this little lemma off to this AI, send that little lemma off to that AI, and you just worry about the big picture and scaffold exactly as you did before. And instead of needing to write a Zulip post that explains what every little sorry that needs to be filled in and waiting for contributors and hoping someone volunteers to take each of the outstanding tasks. Now you just send it to Aristotle and wait a few minutes and, or go to bed. I don't care. I wake up in the morning and see what alpha proof or Gauss or Axiom or whoever have come up with, and sometimes you're lucky. So it's it's kind of funny that it was meant to be an experiment in large collaboration, and it was initially, and now it seems like you individually can do projects like these thanks to the AI tools that are coming online. If all you want is to get the proof. Of course, MATLAB's standard is and should be much higher, and so there's a lot of work. And this is really, I feel very. I have done a disservice to myself because it's going to take a lot of work to get what's in the PNT project into MATLAB over time, and we're getting to work on that. But it's sort of we're moving too fast to. We need to slow down even more than we have, and get things into a form that will be MATLAB ready. Anyway, so as I mentioned, there are lots of novel bits of pure mathematics that we discovered along the way, and I think these will make their way into standard textbooks and become better, simpler, cleaner proofs over time. There's a question of, does any of this kind of work count as research in the mathematics community? We'll have to figure out what the community thinks about that. No one person can decide one way or the other. Okay, let me just pause for a second and see if there are any questions on the PNT Plus project. So far, so good.
Anybody has a question on the first part of the talk?
It's okay if not. You don't have to be shy. Oh, there's a hand.
Hey, Alex, it's Emily Real.
Hey, Emily.
I'm wondering if you could elaborate a little bit more on some of the new mathematics that was discovered on the way. Did this take the form of new proof techniques, new definitions?
Yeah. Well, so I discussed one little innovation, if you can call it that, which is to use rectangles instead of circles, and it makes for a nicer. Instead of these keyhole contours, you just take the rectangle and chop it. But now you have a new problem, which is how do you integrate ds over s over rectangle? And there's actually a very simple solution, very amenable to formalization. So that's the kind of thing I have in mind. Um, you know, these things that when you tell someone who's an expert in the subject, they go, yeah, of course you can do that too. Why not? And you can do that too is something that until you start formalizing and you realize just how impossible, not impossible, again, it's not impossible, just how much more technically difficult it would have been to formalize it the way it's written in every textbook than the way that we ended up doing it. I think there's some value to that information. That's all I was trying to say. Does that make sense?
Any other question? Okay. I think, Alex, you can
Okay.
proceed to the next part. Thank you.
All right, so then let me just say a little bit more about finding novel ways of doing pure mathematics in ways that aren't in the standard textbooks. So, in fact, just yesterday I finished version 0.1. I think that's what you call something that's just barely done, but has a lot of paper cuts and a lot of things that still need to be worked out. So this is the real analysis. I call it real analysis the game. Of course, this is based at the lean game server with modeled on Kevin Buzzard's natural number game. So there's 44 worlds at the end, 138 levels, all your greatest hits, the old favorites, Bolzano-Weierstrass, Heine-Borel, the Riemann rearrangement theorem, everything is some version of everything that you know and love is there, and that's what the scare quotes are about. So let me just describe a little bit what the new versions of these theorems are. So the classical statement of Bolzano-Weierstrass that you probably all know and love is that if you have a bounded sequence of real numbers, it's bouncing around, but it has to have a subsequence that converges. And the classical proof is, okay, so let's say you're bounded, just to keep it simple, in 0, 1. So there's either infinitely many points in 0, a half, or between a half and 1. And then you just keep bisecting, just iterate that, and you'll get a branch where you still have infinitely many points getting smaller and smaller, and there's your subsequence. I just gave you a proof of Bolzano-Weierstrass that's in most textbooks. You want to formalize that proof? I'm not saying it's impossible. It's certainly possible, but you want to formalize it and you want to teach it at the same time. The lean, I think, will get in the way of the analysis when you try to make this argument precise. So, in fact, there's a better, not just better proof, there's a better statement of Bolzano-Weierstrass. I claim that the right way to state Bolzano-Weierstrass is the following. If you have a bounded sequence of numbers, which could be the real numbers, or it could be just the rational numbers. Bolzano-Weierstrass is true in the rationals. If you say it like this, you have a bounded sequence of rational numbers, there's a subsequence that's Cauchy. Okay, so that's something that you can state and prove very, very easily in front of an audience of people who have never seen lean before and people who have just started learning about the real numbers and real analysis. And this proof is very, very elementary. It's in 2 steps. Step 1 is any sequence has what we usually call a monotone subsequence, meaning either monotone increasing or monotone decreasing, what we now call monotone or antitone subsequence. And that's an easy argument about, you look at whether it has infinitely many peaks or not. And it's an argument that's easy to execute in lean. So I used to teach, the class is over now, I taught on Tuesdays and Fridays. And every Monday and Thursday, I dreaded the time that I would sit down to try to work out what I thought was going to be trivial to explain to the class the next morning, because inevitably I would be up until 3 or 4 in the morning until I found a way that I could actually prove what I wanted without a massive struggle and headache. So this is the kind of thing that, again, none of these arguments are really new. It's just putting them together and reinterpreting them in some kind of slightly different way. Anyway, once you know that every sequence has either a monotone or antitone subsequence, which is just a standalone fact, step 2 is if you're bounded from above and monotone, then you're actually Cauchy. And that's also very, very easy to prove. It's a very pleasant argument, just following epsilons, for all and there exists universal and existential quantifiers, and you can do it. So you chain those 2 things together, you get the statement that I said before, and that statement holds for rational numbers. Okay, so Bolzano-Weierstrass is not a statement about real numbers, it's a statement about rational numbers or real numbers. If you, instead of saying you have a convergent subsequence, you say that you have a Cauchy subsequence. So this turned into a pedagogical philosophy that developed throughout the course, which is, you read most real analysis textbooks, and they're building a house. They're saying, here's how you pour the foundation, here's how you put the frame on the house, here's how you run the pipes and the electric, and then you start putting up walls. But actually, when you live in a house, you live in the walls. Hopefully you don't see the pipes that are running underneath behind the walls. And so if you want to learn about how you might go about building a house and why the components of the house are what they are, start putting the walls up. That's what you know, that's what's familiar. You put the walls up and then you realize, oh wait, I'd like some running water. I'd like some plumbing. So we have to break the walls open and put the plumbing in. And then, okay, then everything starts to fall a little bit. So you say, well, we need some structure, so let's add some framing. And then the whole house starts to sag, and then you say, okay, let's lay a foundation. Now, I would never want to live in a house that's built by this process, right? But you would certainly learn a lot about modern home building if you built the house this way. And so that's kind of the philosophy that I eventually came to appreciate in the way that the game was being developed, lecture by lecture. And so the key point is that ideas were being introduced only at the moment that they're necessary. So again, if you look at almost any real analysis textbook, chapter 1 is constructing the real numbers. Of course, you have to construct the real numbers, otherwise you don't know what you're talking about. Okay, except that when I was a first year undergrad and taking my first course in real analysis, the first few weeks was the construction of the real, they said, you think the real numbers are just this thing that you can draw with your finger, and they're not, and let's talk about why not. And here's the construction by Dedekind cuts or by equivalence classes of Cauchy sequences of rationals. And then week 3, you know what? It went back to being a straight line. We never again referenced the fact that we spent all this time constructing the real numbers. We just blew right past it. Okay, so chapter 1 is what are the real numbers? Chapters 2 and 3 are something like sequences and series. Chapter 4 is, how do you do topology in the reals? Wait, topology? I thought this was an analysis course. Why are we doing topology? And only in chapters 5, 6, and 7, when you go to continuous functions, function limits, derivatives, integrals, do you realize the need for topology. And so this is the right way to construct MathLib if you're constructing MathLib. It's not the right way, I think, to do pedagogy. And so compare that to what we ended up doing in the game is pretend you know what the real numbers are. Let's talk about sequences. Let's spend a whole couple of weeks just getting really good at sequences. And then once we're really good at sequences, series are really easy. There's no difference between sequences and series. Series is just another word for sequences, except the sequences you're adding up, it's partial sums. Then when once you prove my version of Bolzano-Weierstrass, now you start asking questions. Wait a second. So you say it's Cauchy, but it seems like the terms are getting closer and closer. Does it actually converge? And then you say, well, not in the rationals. So what is it about the real numbers that makes that bootstraps Bolzano-Weierstrass up to convergence and not just Cauchy? Then we construct the real numbers. Now we know what the real numbers actually are. Then we jump straight to fundamental theorem of calculus type ideas, limits, derivatives, and integrals. And then the most basic question here is, when does a sequence of Riemann sums converge? And it's very easy to prove that if a function is uniformly continuous, then the Riemann sums converge to a limit. Okay, but when do you have uniform continuity? It's easy to prove that if function is continuous on a compact domain, then it's uniformly continuous. Okay, wait a second, compactness. When do you have compactness? And now you spend the time to work out the topology once it's been motivated by a real need. And finally, in chapter 7, you start doing things like interchanging limits and integrals, and so everything needs to be motivated. I have too much ADHD or something. I can't concentrate on something unless I know why I'm doing it. So I would never start introducing topology before we have a question that theory is trying to answer. So that was a slight pedagogical deviation from the way things are normally done. Let me give you another deviation. So here's Heine Borel. What is compactness? Before this class, I would have said, yeah, compactness is any open cover has a finite subcover. It turns out that having an open cover is really, really annoying to work with, at least in the game. It's not annoying in MathLib, but it is annoying in the game the way that it's designed, so that you can just write one line of code at a time and interact with it that way. And I realized that here's another alternate version of compactness. Any cover by balls has a finite subcover by those same balls. It's actually really important to know where the centers of those balls are and what the radii of those balls are. And so here's my version of compactness. And of course, it's easy to prove that that's equivalent to the standard notion, but it's just much easier to work with formally. So for any indexing type, now we have to talk about arbitrary indexing types, which is a really fun moment. This is pretty late in the semester. They've had a lot of experience with Lean and a little bit of experience with what dependent type theory can do. So then you have the sequence of x's are the centers of the balls, r's are the radii. You have proofs that the radii are always positive, and then you have that S is covered, your set S is covered by balls at those points with those radii. Then there exists a finite subset of your indexing set so that you're still covered by the balls just from that indexing set. And that makes it possible to prove all kinds of nice things like Heine Borel, which still is the standard version. So there's sort of 4 things to prove with Heine Borel. If you're compact, then you're bounded. That's very easy. You take the integers as your indexing set and just take balls centered at the origin with larger and larger radii. Those cover everything, so they cover your S, and so finitely covered means you're bounded. Medium difficulty is that compactness implies closed. Let me not go into how you prove that. Then how about the other way around? the proof that I mean, again, everything I'm doing is completely standard. It's just not put together in just this way. If you take a closed interval, then you're compact. That's not hard to prove. And the hardest thing to prove is if you have a closed subset of a compact set, then you're compact. That's the last thing you need to finish Heine and Borel. And here you get to do things like, okay, so you have your set S, which is a subset of T. T you know is compact, S you know is closed, and you want to know that S is compact. So take a cover of S, and how are you supposed to get a finite subcover of S? Well, you just S complement is open, and so there are balls around every point in the complement. So you take your indexing type to be the sum type, both of the original cover and the cover of the complement of S by balls around there. That will cover the entire real line, so it'll cover T, so you'll get a finite subcover from it, and you get to do, you have to do a little bit more work there, but we got to really see the full strength of arbitrary indexing types. And of course, then a student says, well, wait a second, why do we need these arbitrary types? Can't we just index everything by the natural numbers? And now we have a fun discussion about countable and uncountable infinities. Anyway, so I'm running out of time, so I'm not gonna talk about the Riemann rearrangement and the conditional convergence theorem. Think about how you would prove those with both hands tied behind your back. And the real question for me is, okay, I'm glad I'm having fun. Are the students actually learning anything? That's what the course is supposed to be. Are they learning real analysis? I do not care that they have learned lean. Of course, in order to learn real analysis through the game, they needed to learn some lean. And so the null hypothesis for this semester was that students with no prior exposure to lean and no prior exposure to the subject matter cannot effectively learn both. And I have to reject the null hypothesis. So let me just show you what a sample, so there were 2 midterms and 1 final exam. Everything is in class, timed, and on paper. Just paper and pen questions. Most of the questions were natural language, had nothing to do with lean. And a couple of the questions were things like this, where, a sequence diverges to infinity if yada yada. And we have a sequence A that diverges to infinity, a sequence B that converges to L and L is positive. Then C is a sequence that's the product of A and B. Prove that C also diverges. And here's the proof. The student starts writing intro M and specialize. And then, at some point, the student is specializing something to an N, and they realize, wait a second, I don't have the N yet. So I need to use the sum works better than the maximum. And now you introduce the little n, and they put that there. So it really, I think, makes it so much easier to be able to analyze what they're doing when they have the language to be able to do it formally. In fact, I would say some of them preferred lean proofs to natural language proofs. And I think in the future, even in natural language, we're going to start naming all of our hypotheses. And we'll look back at math that was done with unnamed hypotheses the same way we look at 16th century algebra. So this is, you read Viet or even Descartes. You have some unknown quantity. Then you create a second copy of this quantity and combine it with a known amount, and then multiply this total by our original unknown quantity. Then you get a specified result. You want to read that, or do you want to read x times x plus a equals b? In the same exact way, you want to read intro epsilon, use capital N, or for sufficiently large, whatever. You can imagine where I'm getting to. It's just formalization is more efficient to communicate complicated ideas in natural language. Forget about lean. So anyway, a peek into where I hope this will go into the future is that we're in the process of working on a Scratch version of the real analysis game where you can just drag things and pull them in and out. And each level is an escape room. You don't get out of the room until you construct a proof of, a proof term. And the hope is that 12-year-olds will be competing to master these levels on their own. All right, so let me stop there. Thank you so much for your time.
Thank you so much, Alex. I think there's time for 1 or 2 questions.
Thanks. Hi, Alex. It's Filippo.
Hi.
Thank you for the talk. It was really, really nice. So I was wondering, at Rutgers, are you alone doing all these, in the sense that are these students are going to see no lean whatsoever in the rest of their studies, or will they see it again?
So we have an active lean seminar with lots of, undergrads, grads, postdocs, senior faculty. We also have now this semester for the first time, we have an intro to proofs course that's being run by one of our postdocs, Ayush Kaitan, following Heather Macbeth's book, and he'll be doing that again next semester. But this course is at the moment a one-off, and I like to jump around with what I teach. If I taught real analysis this year, I probably am not going to teach it again in 3 or 4 years. I'll do something else, and maybe I'll make another game for whatever else I do. I don't know. This is so much work. I think I'm not eager to. Next semester, I'm teaching a graduate topics course in analytic number theory, and it will all be on Blackboard and chalk and no technology. But you make a very good point. They now have this skill that is kind of not going to serve them in the rest of their undergrad career. Maybe, but maybe it's not the lean that they learned, but the rigorous, how to construct rigorous proofs and follow complicated mathematical arguments, and that should serve them not only in their mathematics courses, but in life, I would like to think.
Okay, thank you. So if there's no other question, I have a small question actually. So I think this game is designed for people who do not know Lean beforehand, right? But maybe in the future we're looking. We hope that more and more people will already know Lean when doing a course. So do you still think that the game format would be useful for people who are already proficient in Lean to learn just to learn new math?
Yeah, if you already know lean, skip the first level and a half. Because the first level is intro and use and choose and specialize. And if you already know that, great. But the next level is limits. And if you don't know what how to say sequence has a limit, then that's where you start.
Thank you very much.